So we're going to continue on discussing differentiability and derivatives. So we talked about the derivative being the instantaneous rate of change of a function. And so now we're going to look at one-side derivatives. Thank you. So if I had something written, this is on page 104. I have something written as limit as h approaches 0 from the right-hand side of, say, f of a plus h minus f of a all over h. This would be, we would call this the right-hand derivative at a. So this would be right hand, color. I'm fine with you guys using the at symbol. So the right-hand derivative at a, that's what this is saying here. And then we have, in math language, the other guy, we have the limit as h approaches, say, 0 from the left-hand side of f of b plus h minus f of b all over h. We say the left-hand derivative at b. What's that? As a limit as h approaches 0 from the right-hand side. This is kind of a curved thing here. Okay.
Oh no.
What's oh no?
I wrote A instead of E.
So examples.
How to make it the whole page.
What's that?
The whole page.
Yeah, that was full screen now. Definitely took some time to make sure that that was done. You guys, some of you may or may not know, depending if you're absent or not, but all the videos and flipcharts are now available on Blackboard. So please feel free to take those directions down. Look at a picture of the phone, that's fine. How to access Blackboard so you guys can look at these flipcharts and videos on your own time. Okay, so example 6 in the text is a good example that definitely is going to be seen on the AP Calc exam, and therefore it'll be seen on exams in this class. Let's say we have So this is the function in purple is going to read, move it over a little bit. We have y equals, and this is a piecewise function. Some of you said you were not familiar with these. So here's a perfect example of piecewise function where y is equal to x squared when x is less than or equal to 0. But the function is equal to 2x, the value of it is 2x when x is greater than 0. So that's what this means. It's saying, okay, the function is x squared for all values of x less than or equal to 0, but then it's equal to 2x for all values greater than 0. So you see there's clearly what would look like clearly two distinct functions. Basically took parts of those and combined them into one function. So if you took the left-hand derivative, say at 0, at x equals 0, and the right-hand derivative at x equals 0, or the exact verbiage they used was right-hand derivative, yeah, exactly that. Right-hand derivative at 0 or left-hand derivative at 0, are they going to be the same?
No. Yes, because it's the same point at 0.
Oh, no, because they're two different.
They're two different things.
Yeah.
If you look at the math on page 104, we see that the limit, write this in say blue, we see that the limit as h approaches 0 from the left-hand side it's going to be 0 plus h I'm not going to the way I wrote that. I'm going to go back and I'm not going to write it like that. I'm going to say the limit of this function, y. This ended up being equal to 0. But then when we took the limit as h approached 0 from the right-hand side of y, we ended up getting a value of 2. So what we would say is that this function, while it is continuous, I can take my finger and keep it stuck on the panel all the way from negative infinity to infinity. While I can do that, the fact is that the derivative taken from the left-hand side at 0 and the derivative right-hand side at 0, they don't match. Therefore, this function would be considered not differentiable. This function is not differentiable. More specifically, it's not differentiable at this point, so therefore we can say it's not differentiable altogether.
Okay, yeah.
I'm a little confused on how you found what y equals.
Me too.
Okay.
How do you know?
So if you look on page 104, yeah, we're gonna. It's a big word, so we'll say let me write that first. So this function is continuous. So y is continuous, but not differentiable.
And that's because they're different functions, but the same function.
The reason is because, in a very, very simple way of putting it, this is not smooth. There's a cusp. There's a sharp turn. Okay? So this here is a cusp. So, right, let's go with orange.
That's what
Let's go with this side.
Or you cannot find the derivative of that?
because
So you can't call it a parabola like this that has a different kind of function.
Well, I understand that it's
Both
not
the
the
sides are different and it's not differentiable.
if you have one derivative,
We call this a
then
cusp.
two different.
Yeah.
I hear this called a
What
cusp.
You can find the derivative.
Yeah, you can find the derivative. So that means you can't find the derivative.
If you can differentiate, you
Okay.
can find.
So here's the question: what does differential mean? Differential means that for a function differential means that you can take the derivative for at any point on that function. And for this function, you cannot take the derivative at 0, so this function is not differentiable. So what makes them a differentiable? What makes a function differentiable is if it's continuous and smooth. So that would be a slide on its own. What makes something
To
differentiable?
find out if something is differentiable or not,
You would just.
It's smoothly goes from each derivative, so that means that if it had a sharp turn, it would be different.
It means to be differentiable. So we'll say one definition is smooth and continuous. And another way to describe it is the derivative can be found or taken at any point. The derivative exists for all points. And I know I hate to throw you guys a loop or anything like that, but we make it just like all kind of basically the same definition because it really is. So it's smoothly continuous, and therefore the derivative exists for all points. So now here, if you look at the math that's done, if you go back to here.
Yes.
Yeah, sure. So again, the function must be differentiable in order for it to have a derivative. So piecewise could be differentiable.
Piecewise, is that just like, how do you spell that? Piecewise?
Piece, it's not
Is it
piece
like-
like piece, but
because
it's
it's
piece like
it's two different functions.
you have this piece
Two
and you have
different
this
functions.
piece.
Okay. So it's like P-I-E-C-E-Y.
Yeah.
Mhm.
Piecewise.
Yeah.
That's great.
It is a weird word. I don't know where the Y.
Everything
I don't know where the Y is coming from, but
Yeah, that doesn't make sense, but.
it might. I don't know. So this is a piecewise. We clearly have this piece of it, and then you have this piece. Now, just because it's piecewise doesn't automatically mean it's not differentiable. This one happened to not be differentiable because we had this cusp or sharp turn. And mathematically, if we could find out that the derivative taken at that point from the left-hand side derivative and the right-hand side derivative, they don't match, so it's not differentiable. So if you want to see this worked out, you can look at the text on 104, example 6. This is example 6 on page 104. Where you just apply the derivative like you normally would, where you have letting a be 0, so 0 plus h squared minus 0 squared over h. And then for the right-hand side, you would use the 2x as your function. So you have 2 times 0 plus h minus 0 squared over h. And we'll be doing a couple of these, we'll be going to these problems now, so you see how you come up with an actual value. It's at a point. It's at this point here, 0. So let's go ahead and look at section 3.1. Any questions about this? Again, cusp is one thing they use. I don't think there's another. If I find it, if I come across it, but I've only seen cusp.
Is that where 2 points meet, or like the 2 things meet? Is that what the cusp
Yeah,
is?
we call it a cusp when there's a sharp, also known as a sharp turn. You see, basically think of it like this logically. How can you go from instantaneously go from what would have a rate of change of 0 to instantly have a rate of change of 2, which is what this is saying. At 0, it changes instantaneously from 0 to 2. And in any case, you can't for it to be differentiable.
Oh, I was like, it did.
Or it would have to be. It would have, these would have to match for it to be differentiable.
So this is not, like, that's not a thing?
It's not differentiable.
This is a function that is continuous,
Right.
but not differentiable.
It can't be like that if it is.
But it is a function, but it's just not differentiable. So let's look at some problems. We have number 1 on page 105 says the limit as h approaches 0 of 2 plus h squared minus 4 all over h. So you're not even necessarily concerned where this came from. They just give you directions. They say evaluate the indicated limit.
So we just,
So we're going to evaluate this. So how we go about doing that?
expand.
Yeah. Okay, so expand top. I'm going to be, well, I'll just go ahead and write it again. Limit, it's going to get sloppy, but this always means limit. Limit as h approaches 0. Of this expanded would be 4 plus 4h plus h squared minus 4 over h, which simplifies to the limit as h approaches 0. 4 minus 4 is nothing. We have 4h plus h squared. Now we can now factor out an h, leaving us 4 plus h over h, which these simplify 1 over 1. So now we just plug in 0. So this whole thing would equal 4.
Oh, wait, because you can make it 0, because it's as it approaches 0. You just make that.
Any question about this?
When you get 4, like, it says 2 plus h squared minus
So you can
4.
only make the H0 without one.
How did I go from here to here?
Not quite, like, how did you get -4 in the first?
This was given.
Oh,
You're talking about that? This is given.
I have a question.
Yes.
I don't understand the whole like making that H0.
Because we want to limit as h approaches 0. So written something like this, something linear, you just plug in 0 for h. That'll tell you where it's approaching. I mean, you can plug in, okay, like, for example, think of it like this. You can plug in a really small value, 0.0001. And this value would be, what, 4.001. You get even closer, so plug in, say, 0.000001.
Why
It would be
plug in one?
plug in 1. Well, because we're not interested in the limit as h approaches 1. We're interested as the limit as h approaches 0.
As close as you can get to 0.
So you would see, naturally, if you made a table, 0.1, 0.001, you know, and so forth, this will approach 4. The limit is 4.
Oh.
Okay, so let's look at another problem. Same page, 105. Say you run into a situation, say you're finding the derivative at a certain point, and you run into a situation that looks like number 4. We have the limit as x approaches 4 of 2x minus 8 over the square root of x minus 2.
limit is
These are good problems for you because typically these are problems you definitely look at in pre-calc. I know some of you may have not covered these in pre-calc, so these are definitely good to look at, especially if you start doing, these are, there's definitely part of the, your understanding for calculus. Your algebra has to be solid. So how can we evaluate this limit? Now, if we plug in 4 right now, you're like, okay, well, I have an issue of division by 0, so I'd have 0 over 0, which is considered an indeterminate form, so there's something we do algebraically. Because right now, this would be 0 over 0, which is considered indeterminate for a limit. Okay, 0 over 0 by itself is undefined. But if it's the value you get from a limit, it's considered indeterminate. This is one of the indeterminates. Indeterminate.
So you just plug in 4.
Yes, if you plug in 4, you derive here, indeterminate, so we got to figure, so basically we say, okay, we haven't figured it out yet. It's from the way we just approached it, it's indeterminate. So it still may exist. It may exist. Let's see. So algebraically, do we know any tricks here?
Can you multiply it by the square root of x plus 2?
Very good. So let's try the conjugate, see what happens. So if we multiply this by, so we have the limit as x approaches 4 of 2x minus 8 over the square root of x minus 2. So you guys know the trick of the conjugate, or you should be familiar with it. Okay, so now this would be like equivalent to finding the limit as x approaches 4 of, what would this guy look like? Specifically, I'm going to leave this guy factored for now, I don't care about them, but let's go ahead and let's FOIL this. We would have something over x plus 2 root x minus 2 root x is nothing, minus 4. Did you guys even see that? Okay. And here we have 2x minus 8 over the square root of x plus 2.
You can factor out the 2x minus 8.
Ah, okay, good. Now you see it. Do you see what she sees here? This is what you're trying to arrive at. Because right now, algebraically, you only really know factoring is really your friend here, as far as these problems are concerned. So this would be equal to the limit as x approaches 4 of, she factored out a 2, x minus 4 times the square root of x plus 2 all over x minus 4. This is kind of like algebraic thinking, graphically thinking. It's kind of like removing that, so it's a hole. It's not an asymptote at 4. So you can find the limit. The limit does exist. So now you can plug in 4 as it reads now. Right? This is a 1. This is a 1 here. So if you plug in 4 now, what would you have? So we've actually simplified this to 1 over 1, so this is now reads 1 over 1. So now you just plug in 4, you have 8. So this limit is definitely equal to 8. And you can actually see it if you graph on a graphing calculator. You can definitely see it kind of verify and make yourself feel, maybe build that confidence to know, okay, I definitely know it's 8. You can also do it in a scientific calculator. If you plug in your value really, really, really close to 4, using this original expression, like 3.99999, and you'll see that, okay, I can definitely see it. And from the right-hand side, if you plug in 4.00001, you would also have that situation where it comes out to 8. It will be 8. Okay, now these examples, again, they're just giving you limits. But let's go ahead and let's take it a step further where you're just given a function and it says find the derivative of the given function at an indicated point. So same page, page 105. Say, let's go with number 1. It says, use the definition f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h, right? You're used to seeing when I first show you this x, which is just a very general saying for any value of x. This is the same exact thing, we're just specifying at some point a, where a is actually a constant, a real number. But you guys see it's the same exact thing, just using a instead of x?
Yes.
Okay. So it's saying for number 1, using this, find the derivative of the given function at the indicated point. So we're given for number 1, we're given the fact that f of x is equal to 1 over x. So if it says find the derivative of the given function at the indicated point, a equals 2. Don't let this confuse you. You can literally think of it as x equals 2. They're just saying, okay, using this formula where a is a specific point, it's the same exact thing if I said x equals 2. It's going to be the same exact word. Okay, so how do we do this? Well, we have to go ahead and plug it in. So here we go. So what do we want to find? We want to find f prime of 2. This is what we want to find. All right, that's a shorthand way of saying let's find the derivative of this function at this specific point.
What is the 1 over x? What is that?
This is the function. The function is 1 over x.
Technically, we don't need that, though.
Right, we're not using it.
We absolutely are going to use it.
And you have to find the derivative.
Yeah, because exactly we have to find the derivative.
You're finding the f prime, which is
You have to know the function that you're finding the derivative of.
Okay.
So what we're going to do is we're going to ignore specifically at 2. We're going to find f prime of x, and then plug in 2 for x.
Oh.
So I'm just going to go ahead and go to the next slide. So we have f of x is equal to 1 over x. So f prime of x would be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So here we go. So f prime of x would equal to the limit as h approaches 0. Okay, f of x plus h. So we have 1 over x plus h, right? Minus 1 over x all over h.
Wait, why are you doing this?
Why am I doing what like what?
This is like a long way.
Why can't you find the derivative easier?
You can.
He wants us to understand that.
There's definitely a shortcut to
The
this.
way we do it is the shortcut.
But this is going to build on your understanding of limits and knowing how to factor, which is important for your understanding of just math in general. But yeah, we will definitely, once we get the shortcut, we can definitely start using the shortcut, of course. But definitely we have this fundamental, because what typically happens in a calc class, and I mentioned this before, is that students will start doing using the definition as a limit. And then months into the course, they completely forget that the derivative is even defined as a limit, because all they know is a shortcut. And so when they go to take maybe say a test or specifically the AP Calc exam, it's almost like a foreign language because it's been so long since they've done it the natural way that it doesn't make a lot of sense.
So that's the formula to find the derivative of 2.
Yeah, so the derivative is defined. Yeah, the derivative is defined. The function is defined as the limit as h approaches 0 of f of x plus h minus f of x over h. And were you here when we discussed the derivative?
No.
If not, definitely watch that video, which is available on Blackboard now, so you have an understanding, because it's going to help you with certain test questions. Okay, so looking at this, how can we get to the point to where we have that removable factor in the bottom and in the top of this guy here. So then we can end just plugging in 0 for h. What do you mean by the next step? The next step might be.
Plug in.
Well, we could plug in 2, but we still have a similar looking situation. So we can hold off the 2 at the very end.
Simplify it.
Okay, so how can we simplify this?
Plug in the opposite.
Get a common denominator
Get
for
the h
what?
out of there.
You want the,
For the top.
Yeah,
Very
get the
good.
h out of the bottom.
This is a complex fraction, right? We have fractions inside of a fraction. To deal with those, we need to work on the top by itself. Okay, so what will we have here? If we work on just the top by itself, we would limit as h approaches 0. Okay, so here, what is the common denominator of these two terms here? This guy and this guy, what's their common denominator?
Wait, I have a question.
Yeah, so the LCD of this guy and this guy, the least common denominator would be x plus h.
Wait, how is that h in the denominator? I thought it was like a separate term because I thought it was 1 over x plus h.
How is this h in the denominator?
Yeah, no, not that one. Like in the top, but in the denominator. I don't understand what.
Because f of x is 1 over x. So f of x plus h, whatever you see in here, you just plug into your independent variable, would be 1 over x plus h.
But if f of x, do you see what I'm asking?
Yeah, I do.
Yeah, I'm confused by that too, but I think
Yeah.
it's one of x plus h is the new function and you're plugging it into 1 over x.
This is a
So
this is a
1
very good
over
point.
your new x is x plus h.
What is f of smiley face? I'm not kidding. What is f of smiley face?
are you saying in this case, or?
Yeah, here's f of x. What's f of smiley face?
1 over smiley.
Thank you. 1 over smiley face. No, this is something that a lot of students get confused on. So your
Okay.
question is good. I'm not making fun of any. This is not me being. Let's be a little cute, but in a good way because it's good for your understanding. So what is f
Oh,
of
I see.
smiley face plus
You
h?
take the parentheses and put it
I'm using smiley face because people get lost a little bit of the x is all here all the time. But what I'm making is whatever this is, you plug it into your independent variable x without hesitating. So this would be what? 1 all over smiley face plus h. That's the same principle here. F of x plus h, you plug whatever this is without thinking into your x. And that's what this would be. Okay, so let's go ahead, let's see if we can combine this and make it one fraction. So we know this. So we have, for this guy to become this denominator, well, we have to multiply the top and the bottom by x. Yeah, so it would be x over x plus h minus, now this guy, well, we have to multiply the top and the bottom by. Good. So 1 times x plus h is just x plus h, x plus h, all over h. Now this is this.
So can we do that?
She's messed up now. Fraction and a fraction.
Now let me give you guys something that's kind of like, it's a very good thing to understand. Could someone graph this? Do you guys know what this looks like graphically?
Can we finish?
If you get
Oh,
small.
that.
You guys should have a general idea of what this looks like.
I'm used to.
No, yeah, I don't.
We used to have the presets and we had to memorize what all the preset functions look like, but it's.
Okay. It's good to have a quick image in your mind when you see something like this. So let me pull that up.
It has an asymptote.
It would have an asymptote, which means the function is not differentiable across the entire domain. But at our point, the derivative might exist because at that particular frame, that window frame, it might be differentiable as long as it's smooth and continuous. So if I say y equals 1 over x, you guys should kind of have this graph should make sense, or maybe even remind you, like, oh yeah, okay, I see the red, that would be 1 over x. That's going to be a vertical asymptote at 0, so this function has no derivative at 0. Therefore, this function is not considered differentiable across the entire domain. But there may be a derivative at a particular point, because looking at, say, to the right of 0, moving on, this thing is definitely smooth and continuous the whole way. And from negative infinity all the way to 0 non-inclusive, it's definitely smooth and continuous the whole way.
So it is differentiable.
Not across the entire domain, because we have this break here.
Only in the part.
Yeah, so it's being very particular with our words. So anyway, so you guys know if you're finding if you want to find f prime of 2, you would know just by looking at the graph that it definitely exists. Because at 2, isn't it smooth? It's continuous, so it's going to exist. So that should kind of maybe, if you're not totally certain of what's going on here, it should build your confidence to a certain level. Like, okay, I know it has to exist, so this is going to work out. Because sometimes it looks nasty, but we'll see what happens here. So we'll keep going. So let's keep going. So this would equal the limit as h approaches 0 of, okay, now this I can write as one fraction, right? That's the whole idea, right? Always gotta watch the clock. That's the whole idea. So we have x minus this whole value, x plus h, all over x plus h. But this is all over the big fraction bar, h. You almost wish you didn't know the shortcut. Because you wouldn't know that the pain is unnecessary. At least for just finding it like that. But it is good to know how to algebra.
Know where it comes from.
So,
Especially if you ever forget shortcuts, but I'll do that sometimes where I won't remember. I don't find something, but I remember, okay, I know that this is what I need to do, but I don't remember what the type of
yeah, because
term for it
you're
is.
going to have problems. You're going to have at least one problem where you have to find the limit of something, and factoring may be involved. So it's overall, it's very good math skills. Okay, so let's continue forward. So this guy would simplify to what? In fact, I'm out of room here. I'm going to go to another slide. I'm going to copy this. I can just copy that. Yeah, that'll work. I think so, yeah.
Let's see.
Yeah, negative h. Oh, it's this. Good job.
So this here would just leave you with the limit as h approaches 0 of just negative h in the top. So negative h over x plus h, all over h, which another way we can write that, instead of saying divide by h, we say times 1 over h. So negative h over x times x plus h times 1 over h.
Isn't it h over 1? No. You have to flip it.
So to divide by a number, the same as
Oh, it's
multiplying
already
by
it's
precipitate.
already.
Yes.
Like, cancels.
So now we look here and say, oh, okay, this is convenient. Actually, let me go red here so it's clear, more clear. So this is convenient. So now we have negative 1, and this is 1. So now it's the same thing as finding the limit. Let me just write it here. Same thing as finding the limit as h approaches 0 of negative 1 all over x times x plus h. And now we can plug in 0, and there's no issue of division by 0. So we remove that discontinuity, if you will, and we end up just getting negative 1 over x squared. So this here is f prime of x. So I think we originally wanted to find f prime of 2. So f prime of 2 would be equal to -1. Now you're just plugging in 2 for x. F prime of 2, so 2 squared, -1 over 4.
So that's what the 2 is for. The 2 is for, that's what they want you to plug in first.
Yeah, they want you to find it at 2.
Wait, that's.
Because remember, what does this mean? This means the derivative at any point x, for any value x, this is the derivative of the function f of x. So if you want to find the derivative at 2, well, there it is, -1/4. Now, what does this mean intuitively, looking at it graphically? If you go back to the graph, if I drew a tangent line at 2, it better have a slope of -1/4. All right. Newton and Leibniz. All right, so let's look at some homework.
Like, seriously? Here's the shortcut.
Page 105.
What do you think about it? Like, we never knew this. Like, we never knew what a derivative really was.
I want to do it myself, but I want to know if it's okay.
Well, she said we didn't need to tell.
Yeah.
Mr. Grant, we just have
Yes?
to solve it.
Are we
I can
gonna
ask
like,
you why.
are we gonna have to send Sarah, can we write it on the same page?
I'm not going to ever have you turn homework, but what I'll do is the day it's due, I'm going to go around and check to see that you did it, and then we'll go over the homework with any questions about the homework. So just be honest with yourself, of course. You know, if you're not understanding something, you need to be aware of that.
Am I allowed to do this work like this?
No. Number 6, good question. I want to see the work done out. We will get to the shortcut soon enough. I know. I know it feels like a lot of work, but it is good for your math skills. And number 7. So 6, 7.
This is due tomorrow.
No, this is going to be due Thursday. Ooh, I like this one. Match the graph of the function with the graph of the derivative shown here. (13 through 16).
Yeah.
Ooh, and 17. 17.
All of them are in green.
You guys should be able to figure out 17 if you think about it. You extend what you know what that is. You know it's at that point. You should be able to handle 17.